Hey everybody, hopefully you're here to hear me talk about event-driven collaboration. So what I mean by that, I mean the topic of when we want to use events to integrate between two processes, and mostly often nowadays it's between two microservices. And what I'm going to look at is why you might want to use events over requests, and I'm also going to look at how you actually get it right. And there are a number of things that will come up for you. One is basically what happens, how do you stop going back from events to requests? You receive a notification from another system, doesn't have all the data you want. How do you stop making a request on top of that? And the other topic we'll talk about mainly is producer-consumer correctness. But we'll cover a lot of territory, but those are the big things you should take away. So that's not what you're after. I won't be upset if you leave. All right, who am I? Most of this is dull. It just says I'm old. And it says I work for a company, not a consultancy, so I'm not selling anything. Down the bottom is the bit I always kind of point to. I don't think I'm particularly clever. I'm quite hardworking. That's about it. I got into speaking because when I started a .NET user group in 2003, there was no one to speak. No one came. There's no one from Corp to come and give us talks. So we just did every week. It was every month. It was kind of who's talking next month. And as a result of that, I got used to standing in front of people and talking. And it's just a confidence question. But all of you could do what I do. And I really encourage you to get out and try it. It's great for pushing yourself to really understand a topic and to get into the depths of it, to make sure you feel comfortable being the content on the stage. I work on an open source project called Brighter. Seeing as this is to talk about events, Brighter basically will do two things for you. It'll do what something like Mediator does. Anyone use Mediator? Any of you? So basically it does, effectively takes a command, sends it to a handler, all right? So you can separate between basically the command and the execution to build a layered architecture, for example, a clean architecture. But it'll also do that with, rather than in process, it'll do that out of process. So you can send basically a command or event to another system. Right. So we compete with mass transit and service bus. We are very welcoming. If anyone wants to come and start programming, basically messaging, feel free to join us. We are very happy. Gitter, we have a channel on Gitter, and that's probably one of the best places to kind of interact with the team. Okay. What am I going to talk about? I'm going to talk about an idea called data on the inside versus data on the outside from Pat Helland. Kind of a bit of background around microservices and ownership of data. It'll become important to us as we go through to understand those concepts. We won't actually talk about integration styles because it's a bit of a shorter talk today. We'll then talk about requests versus events. We'll compare the two kind of architectures, request-driven architectures and event-driven architectures. And then we'll talk about two notions that will be important to you. One is the notion of pipelines, and the other is the notion of reference data, or event carrier state transfer, and then we'll talk about correctness, and maybe we'll have 5 minutes for questions. If not, my DMs are open, or come and find me. All right, data on the inside versus data on the outside. So this is my kind of potted history of microservices, and there's a reason why I want to tell you about where I think microservices came from. And that's really because some of the most important literature, I think, on microservices comes from SOA, not microservices itself. So what happened was, once upon a time, there was someone called Don Box. And Don was essentially very much involved in Microsoft's RPC technology for objects called COM. And particularly DCOM was a way of calling between two processes. The trouble with DCOM was getting it working was horrible. You ended up eventually just saying, I'm going to open all the ports on this machine and finally DCOM will work. Of course, that isn't very secure. And Dom reasoned that what he could do to solve this problem was just try and put that communication over port 80, because most machines have port 80 open so they can receive HTTP traffic. And so what he did was he said, I can create an XML payload on an HTTP message. And what that XML payload will say is, I want you to call this method on the other object, and I want to give you to give it these arguments. And he called it the Simple Object Access Protocol, or SOAP. SOAP led to the creation of web services. It exploded far beyond its original intent, which was to solve the problem of DCOM-based communication, and led to us essentially saying, hey, we can have HTTP-based RPC servers, which are effectively serving these XML packages and payloads. It was huge. Large numbers of enterprises then began to orient around basically these service-oriented architectures. And after a while, people learned, which we're about to have to relearn, unfortunately, that request-driven architectures had problems, which we'll talk about a little bit later. And so they moved towards events. So SOA2 came along, which was basically saying, let's not use a request-driven architecture, let's use an event-driven architecture. Now, the problem with SOA2 was by this point, all of the software vendors had got wind of the fact that everyone was doing SOA and everyone was trying to use events. And they wanted to make some money out of the process. So they created this idea basically of the enterprise service bus. And the enterprise service bus was this thing that lived in the middle, at the heart of your enterprise, and took messages in on one side and routed them to consumers on the other. But on the way, did translation for legacy systems, built workflows. What happened over time was a lot of the smarts, so the business logic and the application, moved into the enterprise service bus in the middle. And the individual services were really little more than CRUD wrappers around entities. And the interesting logic had left your services and got trapped in a proprietary piece of software that was very hard to get under test and very hard to reason about. So as a result of that, a ThoughtWorks employee called Jim Weber created a movement called Guerrilla SOA. And he said, what we need to have is the logic needs to live in the services, and the plumbing in between should be as dumb as possible. You should just use REST or a lightweight broker like Rabbit, right? And so essentially he created an idea which Martin Fowler and James Lewis, anyone see James talk earlier in the week? He's around. James is one of the fathers of microservices, but I don't think everyone guesses that, called smart endpoints and dumb pipes. So the idea was remove all the complexity out of our pipe work and put it back in the services. The services should hold the domain logic. And then what happened is that idea got taken forward by people like Martin and James, mixed in with modern ideas like domain-driven design and DevOps, and that created microservices. But microservices is really something you can think of as SOA3. There's also an influence of people like Adrian Cockcroft over at Netflix doing what he called fine-grained SOA rather, in reducing the size of any given service in SOA. But there's a direct line of travel along them. So one of the things to bear in mind is there's a lot of smart thinking done in the SOA era about how to make these kind of systems work. Much of it is still applicable. And particularly today, a few of the ideas we're talking about come from a guy called Pat Helland, who worked at Amazon and Microsoft. And he came up with some very interesting ideas about SOA. So when Don Box defined what was to become SOA, he came up with a thing called the 4 tenets. And the 4 tenets are kind of rules that any service needs to obey. And the first rule we're going to talk about is this one over here. Let me see if I can get this working. Is boundaries are explicit. Right. What does that mean? Well, it means that your service should have an explicit contract with everyone who depends on it. You want that contract to be stable, because I don't want to force everybody else in the organization to rapidly have to change their services every other day because I've changed my API. So what you want to do is say, I want a nice stable HTTP API or the like to work from that is basically not going to change too often. But the API may be HTTP, it could be gRPC, it could be an AMQP or Kafka message. It doesn't really matter what the format in the message is. I've got a stable, fairly long-lived contract with the rest of the world, right? And nothing gets to talk to anything inside that boundary. Okay, and that leads us to the second property, which is services are autonomous. So I must be able to deploy my service without impacting anyone else. No other dependency needs to be shipped at the same time. And that gives forth this idea that I own my own database. And when we say I own my own database, it doesn't have to be the server. It could be a number of tables in the server that only I can access. But I have to own the schema and I have to own the data in those tables. Everything else has to talk to my explicit boundary. It can't penetrate to talk to my service. That means I can ship my service because no one else is depending on the shape of the data in that table. And I can change as much as I want, and no one else will have to basically reship their service at the same time. It also means I can change any of the code inside my service because no one's dependent on it. So what you don't want to do is expose, for example, your domain objects directly here. You want something called an anti-corruption layer in between that enables you to essentially keep changing your internals, but maintain the contract you have with the outside world. And that's what allows microservices and SOA services to be released on their own tempo without concern for other services in the enterprise. And that gives you basically agility and velocity. The other two are slightly less important to the conversation. They are share schema and not type, which essentially simply says don't share things like types depending on your given language, because one advantage of microservices or SOA is you could write this in any language because you've got effectively a well-known standard usually for your boundary. So it doesn't matter if I've got .NET, Java, Haskell, or whatever inside, because what I'm going to share is something like JSON or XML or another protocol over the wire, protobuf, for example. And so everybody else basically just reads that particular policy of data. Right? And the last one that's important for us is compatibility by policy, which means things like I'm going to use OAuth for authorization, etc. It's how do you talk to me in an effective way? But what we end up with is my service is essentially a single writer for this data. The only person that can write this data is me. If you want to write that data, you have to call me via my API to do that. So Pat Helland took that idea and he said, there's some interesting characteristics once you do that. So imagine that I decide to call my API with a get. And let's say, so the example I'm going to use here is hotel bookings, which I know absolutely nothing about. So I apologize to anyone who works in that domain and can explain to me quite why I'm wrong. But imagine I want to get a list of bookings from my bookings microservice. So I can do a get, and I can pull the data out. Or maybe I'm raising an event. Someone's done basically a post into my service, and I'm raising an event telling anyone who's listening that I've got a new booking created. Now, these pieces of data are interesting because that's how data effectively is leaving our service. It's also how we change by doing a post, right? And we can look at this data and notice it's got a number of interesting properties. The first is that the data that leaves our service is immutable. There is no point in you taking the JSON response that you get from your get and altering it, because the only way to alter the data is to be inside the boundary and write directly to the database, or to call me, for example, on an API that asks me to do that for you. So this data essentially is immutable. Same with the event. There's no point in you mutating the event body, right? It is essentially read-only for all purposes. It is stale. As soon as the data leaves my boundary, there's a risk that effectively that it is no longer correct. That is because as soon as I do this get to get, for example, booking 1, 2, 3, 4, 5, there's nothing to say that a post doesn't come into the API and alter the booking. This data, which now exists on the wire, the consumer has presumably read that get data, is now inaccurate because essentially it is behind the system of record. So my data is always stale. This leads to the idea of what we call sort of, eventual consistency, but data leaving a service always becomes stale the moment it leaves the service. And as a result of that, we typically version that data. So on the web, something like last modified or an e tag is essentially a version of the data. It says this data was effectively last changed at this point in time. An e tag would give you essentially a code that says this representation of this data has this ID, and if you have the same ID, you have the same version of the data. And we effectively sometimes say, well, here's how long we think you can keep looking at that data before it's probably worth you checking to see whether you have the current copy to see if it's changed. Until that point, look at the version you've got. But after that amount of time, maybe you should check back with us and make sure that no one's updated the data and there's a newer version of the data in existence. Same is also true effectively of my event. I can put a version stamp on this and say, hey, which version of the is this event? And you can say, is there a newer one? So this data essentially is immutable, stale, and versioned. All right. So the single writer here, and data leaving the system, immutable, stale, and versioned. And Pat called this data inside data, data inside our boundary, and this data outside data, data which essentially has left our boundary and gone somewhere else. Right. So, and the white paper is called data on the inside versus data on the outside. If you want to go and read the original white paper. And the way we tend to scale in things like the web is we cache that data. It turns out that essentially one of the properties of outside data is because it's immutable, stale, and versioned, it's very highly cacheable. So if I do a get to booking and I pass in an if modified stamp, I'm saying, give me a new version if there's one after this point in time. And what happens is, effectively, we'll say, okay, I can give you back a 304 not modified, if essentially that's still the latest version. Or I'll give you a 200 and a newer version with a newer last modified timestamp if one exists. And essentially, from, say, my browser, I've got a range of caches I can hit and ask that question of, right? So I've got a cache locally in the browser, a forward proxy in my enterprise, and a reverse proxy effectively on our side, effectively the business, basically sitting in front of our APIs. And that lets me reduce latency, because I'm likely to find a copy in a cache closer to me, up until really the point where effectively I need to revalidate and check that I've got the current version. And so we use caching to scale a lot and prevent us having to go back from the browser every single time and make a request to the origin server. A lot of the time, I can just get the answer out of a cache. Right? Okay. Right. So park that information in your heads. We'll come back to that bit of information again in a little bit of time. So when we start working with microservices, and when we're working with microservices correctly, and we say this microservice owns its own data, one of the problems we're going to hit is what I tend to refer to as the join problem. So imagine I have my imaginary hotel booking system, and someone wants to book a room in my hotel, and they are a customer who has an account with me, and all their details are on file. So they call my API, and my API says, I'm going to make a direct booking. The direct booking system says, right, I'm going to store the direct booking into the database, and I've probably got to retrieve some information as well, like the account details for that given customer. When I've got the account details with their credit card information and their address, I'll send it to my payment system, and my payment system will take a payment off PayPal or whoever my payment provider is, and then I'll store information in the database to say that that booking has been successfully made. All right? And then I can go and inform some other systems like housekeeping and channel manager, which are all just basically modules in my monolith. And what's going on? Channel manager is when I'm talking to things like booking.com, etc., and saying, update the number of rooms I have available on a given date. Okay. And that's what we were all used to in the world of monoliths. When I get into the world of microservices, if I assume that many of those individual modules are likely to actually end up being microservices, I now have an interesting problem by the rules that we've given earlier, because direct bookings is not allowed to talk to the database in credit card payments or accounts. So I can't reach in and grab the data. So maybe what I can do is talk to the API on the other systems, right? That's their boundary, so I'll make a request, I'll get the data out of the system and be able to work that way. All right. So let's talk about that strategy. One of the problems with that strategy is that when I make a call to all these other services, it's a bit like making a telephone call. So you pick up the telephone, if you still make telephone calls, I know it's becoming less frequent. My mum phones me, but nobody else ever phones me. But if we remember making telephone calls, I pick up the call and I call you, and what needs to happen is you need to be there to answer the phone. If you're not there to answer the phone, it's a bit of a problem because I can't get through to you now and we can't resolve whatever we needed to resolve. And request-driven architectures are a bit like telephone calls. I'm making a call to another service and saying, please pick up the phone and do something for me. And there's a problem if that service is not available. So if in your environment, for whatever reason, channel manager was down, either due to failure or routine maintenance, the problem is I now can't complete the operation because direct booking's call out to channel manager is going to fail. If I've written it naively in a transactional way, I may now just fail the whole booking because I can't talk to channel manager. And even though channel manager might well be optional, so I might say, fine, I'll just ignore the fact that I can't update basically all of the aggregation sites with the new availability of my rooms. If I can't talk to accounts to get your account data, then how can I take your payment? If I can't talk to credit card payments, how can I get you to pay for the room? And this transactional idea that we have taken from our original monolith doesn't play very well in the world of request-driven, in the world of microservices, because they end up bound to this request-driven architecture. And this problem is known as temporal coupling. We are coupled to the availability in time of the other service, right? I've seen Ian Richards and Jim Weber call it emergency services because it's great when you call them and they're there. But if you call the emergency services and you don't get a response, then you're in real trouble. And that is kind of the problem. Now, we can solve this problem a little bit, right? So what we can do is say, well, rather than have a single instance of any of these services, I'll have many instances. And it's the same thing with me calling your business. Rather than you having one phone, and if no one's at the reception desk, you don't get my business. You have a call center somewhere, and you have loads of people who can answer the phone instead, right? And so that's what we do. We increase the number of instances. We put them behind some kind of proxy. The proxy effectively load balances to that upstream group. We may choose to remove unhealthy instances, and that effectively is how we begin to get towards this idea of a service mesh, right? Once everything's going to the proxy, I can monitor the proxy, I can create control planes and data planes, but all that's trying to do is say, this is an inherently unreliable architecture, and in order to make it more reliable, I'm going to have to increase the number of instances of things in order to create some reliability. Events provide an alternative solution to that problem. In events, what happens is I say, well, when I get a booking by direct booking, I'm just going to raise an event, and I'm going to signal to anyone downstream who wants to subscribe to that a booking has been made. I don't really care what happens, because I believe that eventually the right thing will happen. So I just raise an event. I don't care about your availability. Right? The direct bookings raises its event, and what it does is it raises it to a topic. It doesn't know about the physical location of any of these services. It doesn't need a proxy to route to them. It just says, I'm raising to the direct booking made topic, and anyone who subscribes to that topic can pick up the message. So a channel would subscribe to that topic, and then it gets the message. And the big advantage usually a way event systems tend to work is that we use queues to consume from the broker. And a queue will store messages for us until we want to process them. And that can be useful for smoothing traffic, but its primary benefit is that if something like channel manager is not available, because essentially of a fault or routine maintenance, we can just queue up the messages. And eventually, channel manager will essentially come back online and it will begin to process that work. So if request-driven architectures are making a phone call, event-driven architectures are using WhatsApp or Telegram or Slack to talk to each other. Because essentially I send you a message and at some point in the future when you are ready, you answer that message and look at it, right? And it's guaranteed delivery because we say what happens is eventually you will be able to get to that message. Guaranteed delivery. Right? And that gives us the ability to create availability at lower scale. I don't have to throw thousands of instances at the problem because essentially I rely on the broker to give me that availability instead. Okay. But here's when a lot of people have made that part of the journey, and we go, hey, great. I've heard everyone talking at Build Stuff. I know that I should be using an event-driven architecture, not a request-driven architecture. This is awesome. I'm going to raise a direct booking made event, and I'm going to listen to it in credit card payments, and I'm going to take the customer's payment from their account details. And then you go, how do I get the account details? Because if I have to make a request to accounts in response to the notification that I have basically the direct booking has been made, I have just taken my fantastic, reliable event-driven architecture and turned it back into a request-driven architecture. So it was all kind of pointless because essentially I have now got temporal coupling once again. And I've seen a few people talk about saying, oh, you raise notification and then you go and query the other system for the data. The problem is you don't benefit from events when you do that. Okay. So what do you do? Because there is an answer. I'm not going to say it's all dreadful. Right? You wouldn't have come if I didn't have an answer. Okay. So there are two different options. Looking down in the bottom left. So one option is that when I receive the message in my payment system from direct booking made that tells me a booking has been made, when I crack that message open, it's going to have all of the data I need to do the work, which would include the account details that I need from the customer, their credit card, and then UKB postcode and first time address. Not, I guess it's similar here. So optional one is, and we tend to call this a document message as opposed to a command or an event message. Option one is all the data is in the message, and we'll explain in a second how it gets in there. And option two, up on the right, says when credit card payments receives the message, it already has a cache of the data it needs from accounts. So it just goes up and looks locally in the cache, same as your browser looks locally in the cache when you're browsing web pages on The Guardian or whatever you guys get your news from, right? I go and read from the cache. And again, we'll explain how that cache gets populated in a second. All right. First option. So all messaging systems are essentially a pipes and filters architecture. I have a data source, in this case, direct bookings, and I probably have a data sink. What is the end of the operation sequence that I want to perform? And like all pipes and filter systems, in between, I can insert an arbitrary number of steps. And the sender doesn't have to know anything about what the steps are in the sequence, and neither does basically the sink. All I have to do is essentially make sure they subscribe to the right topics. So in this particular case, the common solution to the problem is that direct booking says, I have got a direct booking. And it publishes to a topic called something like direct booking made. And accounts listens to that. And it says, great, I know a booking is, it's probably direct booking made an account, because there may be direct booking made as a guest or whatever, right? I have heard a direct booking made an account message. When I receive one of those, what I'm going to do is crack that message open and enrich its content with the credit card details, the first line of address, whatever I think needs to be added so people downstream of me can process that message. And having enriched the message, I now broadcast something like direct booking with account details. And that's what essentially credit card payments listens to. And credit card payments picks it up, cracks the message open, and it's got everything it needs to process the details. So this is a really good solution. People go to the next one quite a lot, which we're going to talk about in a second. But this is a really good solution in many cases to the problem. Pass the information down the wire. Now, when we just use a series of events, go into individual topics, we tend to call this basically choreography. What we mean is nobody is in charge of this pipeline, right? It's a classic problem with pipes and filters architectures. No one's in charge. No one is managing the steps of the pipeline. We're just relying on effectively, I raise an event, you raise an event, they raise an event, and work gets done. It's a great solution. Sometimes you have a flow that's uncomfortable with. You have to make some branching decisions. You care a lot about failure. And that's where effectively the other option, which basically is orchestration, comes in. So in orchestration, typically at the top level, I receive some kind of request like direct booking. And I effectively have a state machine. And the state machine says, well, the first thing I'm going to do is save that I've got a direct booking request. And then I'll talk to the direct booking system, right? And I will say, hey, make a direct booking, and it will store direct booking and respond to me back with some kind of ID saying, hey, I've stored a direct booking. Then it says, right, now the next thing I know I have to do is add the credit card information to that. So it will then call accounts, and it will add the account details into the message. And then the workflow at the top in basically API Gateway says, great, now I've got the response back from the account system with the customer's details, and I can go and effectively take the payment. And this is basically when people talk about a saga, this is all a saga is. A saga is essentially managing as a state machine a pipeline of work in order to move a flow across a number of microservices. And the advantage of this over the prior one is you can see, well, if effectively I can't find the customer's details on account for some reason, or essentially I can respond to the API gateway and say, hey, there's a problem, we couldn't find this customer's details. If the credit card payment fails, in the workflow I can say, right, the credit card has been declined, take the next step, which may be effectively decline an email. And at any point, usually I have some interface that lets me manage the process and say, hey, I can log in as a customer care representative and see effectively that the state of this particular booking is currently in getting account details, payment was tried 3 times and failed, etc. Right? So that's when you want to essentially take more management control of the process. Always, I would recommend start with choreography, because choreography essentially doesn't require a centralized component, so it's much less coupled and therefore more flexible. Only move to orchestration if you need it, or sagas if you need it. Okay. There's a little bit of a people rush to use sagas because particularly they've got a cool tool that does sagas for them. But start with orchestration; it may save your needs. All right, that's option 1 basically. So I fill the document message with all the data it needs to be processed in a later microservice. Right, I'm passing it down the pipeline and enriching it. Option 2 is to look at this idea we were talking about earlier of outside data and inside data, and the suggestion that there was some of this outside data is highly cacheable. And this idea this is the idea called reference data. So reference data says some of the outside data may be hugely valuable to cache downstream to answer future requests. And it's possible when we have an event-driven system to essentially, rather than have a model that says, well, I go and get something, and after I've done a get, I store something in case I need it again, creates the problem that only works if you get a good cache hit ratio. People keep coming back while the cache has still got the contents in. To build the cache ahead of time, by rather than pulling and caching things, by pushing to the cache. So if I have an account system, whenever a change happens in that system, an account is created, an account is changed because the customer updates their address or their credit card details. If I raise an event from the account system to say something has happened and you may be interested, downstream systems can listen for those events and build their cache ahead of needing to use it. And this has been dubbed by Martin Fowler now event carried state transfer. Right? And the idea is accounts says, I've got a new account. My little worker process running as part of my credit card payments microservice says, oh, great, I'm going to basically add that account into my account's cache. It says, oh, somebody's updated their credit card details. They got their last credit card expired. I got the new one. Great, my worker process listens to that message and updates my local cache and accounts. Someone moves house and they change their address. I update my accounts record for them. So essentially, I have a copy of the information I care about from accounts. I'm going to have all the data, right? From the point of view of credit card processing, there's only a certain amount of data I care about, and maybe lots of other data in accounts that I don't care about. So I only store the bits of the data that are important to what I need to process it with later. There is an issue. Yes, we're duplicating data. This has become more common since storage has become much cheaper, right? So this whole model has emerged much more because of the cheapness of storage. But that now means when effectively credit card payments receives an event saying a booking is made, it can simply ask its local account store, well, what's the customer's credit card details? And get the data locally. The other advantage is, remember we talked about caching on the web, we now have much lower latency because essentially this database belongs to us. And so we're not making, say, an HTTP call to go and get the data. We also have built what's called a bulkhead. And that means in the event that the account system is down for a period of time, we can still take bookings and make payments because we are not dependent on it being up in order to read account information. So everything we need to fulfill our role inside the business is part of our microservice. And that means a failure here doesn't ripple out across your entire business. That's a bulkhead, right? And so events, and particularly caching reference data, provide bulkheads to failure in the organization. And in turn, credit card payments may raise its own events and may listen downstream. Always use the full event rather than the delta, because that enables you to essentially cope with out-of-ordering problems by just taking the latest version and discarding ones that are out of order that were earlier. Okay. Right. Okay. So generally speaking, the most common way that we in the past we do this nowadays is by events. Just for information reference, it doesn't have to go via events. Once upon a time, the most common methodology to do this was atom feeds. Why atom feeds? Well, if I take HTTP, right, and I basically expose all of my events via an atom feeds are very highly cacheable because any page after the current page is immutable, guaranteed to be. So I can read back pretty easily and find the first modification by looking at a page with an E tag I haven't seen yet, and then read forwards from there basically to get any events that I haven't seen. So in the event that you don't have message-oriented middleware, atom feeds are quite a common one. Vaughan Vernon uses that a lot in implementing domain-driven design, I think, so you can read more about that if you want to there. ETL, huge numbers of banks over time did this by essentially extract, transform, and load, literally replicate that database from its origin into basically the service that wants to consume it. Only problem with that is I have to have the same database technology on both sides, right? If you do, that is a cheap option to get this done. And in some cases, with really slow-moving data, you just FTP it, right? And everyone goes FTP, but really we're just talking file transfer. So a common use case today is I stick it in S3, and somebody else reads it from S3 because it's slow-moving data. So different strategies. We're mainly talking about events today, but just be aware of what they are. There are different types of reference data, operand data, shared collections, and historic artifacts. Shared collections are the main one. So certain data within our enterprise tends to be commonly used by nearly every single microservice. Things like lists of users, lists of supplier accounts, product lists, etc. It's very common to share those by reference data over, say, enriching a message in flight because everybody tends to need it. Operand data is stuff where I want to make a request to you. I need to understand what a valid range of options are, quite often things like products, for example, product catalogs, operand data. And historic artifacts is really an outlier here. That says I can build essentially an analytical system, for example, a big data system, by effectively taking events and building that system. So obviously if I've got multiple microservices, all with their own data, how do I collect that data in order to do analysis on it? Well, I listen from events from all the systems and I collate the data from the events, right, via a data ingestion pipeline. And that's how you tend to build a lot of big data architectures. You can also use it for a thing called a composite view model, which is when essentially you say, I need to basically do a get from my mobile phone, get loads of data at once, so don't make 5 requests, and you can build essentially a store that effectively collates all the data and has therefore a very low latency to grab it all at a get request. Right, a couple of quick rules. Remember essentially that reference data is outside data. Don't expose directly off your database as an event for downstream systems to catch just the contents of your database, right? It needs to be essentially a contract that you have defined that you will honor for a period of time, the same as it would be if you made a GET request to that endpoint. What I tend to do with reference data is think, if I called you via an HTTP GET, what would you give me? That's probably what I should be raising as an event onto the wire so that you can collect and store that. And in particular, what you want to avoid is, I don't want to know the the rules that you have about interpreting that data. So if you give me a postcode, that's fine. I know what I want to do with the postcode, right? If you give me some complex structure where effectively I have to understand the rules of how to process it, I'm now coupled to those rules which belong to your microservice. And in the same way, if I did a GET request to you, you wouldn't give me all the data and then say, in the front end, you've got to interpret that by the rules, right? You just give me the results. Then the same way here, you should just give the results back. So a typical example at Just Eat is we have a thing called polygon data, and polygon data is where a restaurant can deliver to, right? And typically, I don't want to ship the polygon data to you because the request you normally ask is, can I deliver to this particular address? And that's much more what you cache. Okay, correctness. There's a problem with ECST that you need to understand how to fix, and that's this. If I've got a service and that service essentially updates my local state, I am the single writer, there is a danger, and that danger is when I try and write to my message broker to send the message downstream, I fail to do so. Now, failure could be one of a couple of things. It could be I genuinely fail, or it could be that I succeed, but the broker fails to tell me that I've succeeded, right? But either way, there's no guarantee I can always write to the broker. So that would mean essentially that I would get out of sync because I would have orders or bookings here that weren't seen downstream. And that means particularly caches are now basically stale and out of sync. So how do I fix that? Well, the problem is that essentially nowadays there is very rarely a distributed transaction controller that applies to both the technologies I'm using. They quite often come from different vendors. And also, distributed transactions have fallen out of favor because they don't scale very well. So there are three main strategies you need to understand. The first one is the outbox pattern. And the outbox pattern simply says, if I have a database that has ACID properties, in other words, supports transactions, as well as writing my change to the booking, or the order in this case, I write to a thing called an outbox table, and I put the message that I want to send on the wire. And then the way I tend to do it is you write to the message broker, and when you put this in the outbox table, you put a timestamp in and say, this is when basically I wrote to the table. When you've written to the broker, you update that table and say that's when it was dispatched. And then an out-of-band process, a kind of sweeper process, runs in the background and looks through this table and says, can I find anything that hasn't been sent for more than about 2 minutes? In other words, it had a dispatched, or had rather a written to the table, but it's got no dispatched. So this update has failed, or this send event has failed. And in that case, I will resend it. It just comes along and resends any message that we failed to send. And there's a risk. The risk is that I sent it, but the update failed. So that's what we tend to talk about, basically guaranteed at least once delivery. Because downstream, I may send you a duplicate, because there's no way of me knowing if I sent it to you, but my update of the outbox table to say it was dispatched failed. That means downstream, you have to be either idempotent, able to process the same message twice, or essentially you have to have an inbox that says, what messages have I seen? If I see it again, discard it, right? And that's the outbox pattern. Second option is log tailing. So sometimes it turns out not all databases today support basically transactions in the ACID sense. Like if I'm using MongoDB or something like that, I don't have that option. So one option there usually is that most of those services will expose their transaction log. The transaction log tells me about all the writes to a given table. I can generally process that transaction log. So what I do is I write to my orders table and then I listen to the transaction log. And as I see new writes come in, I then send them out to the message broker. So I effectively use the transaction log as a queue of work to get written to the broker and just keep retrying until eventually I send that next item in the list. Right? And again, because I can't guarantee that I just didn't get a notification back from the broker it was sent, I could get duplicates. So log tailing is commonly used with things like DynamoDB, etc., and that kind of thing, right? Because we can't guarantee. State change capture is the last one, which effectively says I just write to the message broker and I keep retrying until I've sent it or I fail. And then what happens is I update my own state by listening to the message, by subscribing to the message I've sent. It's very cheap and very effective. The only slight risk with this one is you can get sometimes the downstream gets updated before the upstream does. So basically, I take your money, before your booking gets acknowledged, which upsets some customers. But otherwise, state change capture is a kind of lowest infrastructure problem approach to solving the issue. All right, it's into the final bit, logs versus queues. So when I'm exchanging data between two systems, if I use a shared queue technology, so RabbitMQ, SQS, technologies like that, what happens is I put it onto a queue, I read it from the queue, and when I ACK back to the queue to say I've received it, it's deleted off the queue. And the only slight issue with that is what happens if I want to basically replay all the messages from AccountsDB to rebuild the cache, either because I've lost it for some reason or because I've introduced a new service that also wants to cache account data. My only real option is to replay the messages out of AccountsDB, sometimes by effectively faking in the outbox that essentially it's been dispatched. So I just delete the contents of that column, so the super goes, I better resend all those, right? So I replay from the outbox, but that means essentially everybody who's already seen that message and used to build a cache has to know to discard it, and has to say, I've already seen that. Creates a lot of traffic on the wire because you're constantly playing that stuff out. Now, there are ways around it. You can have very tailored queues to actually use to do the backup for the cache. That's a slight problem with it. So message log, which is technologies like Kafka, what they do basically is they say, well, what we do when we send the message is you read the message basically at index 0 from your consumer. Then you read the message at index 1 from your consumer. Then you read the message at index 2 from your consumer. But effectively, we don't ever delete the message. It just lives on that log. That means a new service, you can just spin it up and it will say, I'm going to start reading at 0. And it will read effectively the messages. Now, the advantage of like Kafka, which has a compaction technology, is that Kafka can be told to only store the latest message for a given entity. In other words, if I have 80,000 accounts, at the most I'll only have 80,000 messages basically in the queue, which means it makes it fairly straightforward to build new downstream caches basically out of that technology. So overall, for ECST scenarios, Kafka is basically probably a slightly better bet than something like SQS or RabbitMQ. This gives rise to the problem, by the way, that if you want to start a fight on Twitter, this is what you do. You go onto Twitter and you say, hey, I think that Kafka could be a really good technology to use for event sourcing, right? This starts a fight. So what happens is people get event sourcing and event carrier state transfer look a little bit alike, right? Because with event carrier state transfer, I am sending messages downstream to build, essentially, I think there's a projection of that data that something else can query as a read-only store. So the goals of the two projects seem very similar. Send events, build projection, right? But event sourcing is about inside data. And ECST is about outside data. And they have slightly different characteristics. And Kafka's really good for ECST. That's the problem they're mostly trying to solve. All right. Yeah, so register sets the index. And outbox required only for correctness, right? Yeah, you may still need an outbox even with Kafka, because essentially you still have to guarantee you put something onto the wire. And a lot of the message log technologies will dedupe for you. All right. Okay. That's me done.